Hello, good morning. How's everyone doing today?
Hi, Professor.
Hi. Just 1 second. Okay, so we will continue to talk about how to calculate different forces and how to put it together to solve Newton's second law problems today. We were talking about static and kinetic friction. And we talked about how static friction will change depending on the force that's acting in the opposite direction. But kinetic friction is always a fixed value. So let's review them real quick, looking at the incline problem where an object, the frog, is sitting at rest on the ramp. It's not slipping down. So we know that the frog has no acceleration. All the forces must be balanced, right? So if we look at the force in two different directions, now let's say along the ramp is our positive x, and pointing perpendicular to the ramp upward is positive y. You can always choose it the other way around, right? You can choose it this way, or you can flip y to be downward, so that's all fine. So if we look at the forces that's on the frog right now, if you draw the free body diagram of the frog, you would say it has weight. I'm just gonna call it weight, so it's easier for me to break it down into components. Weight of the frog, and I have normal force of the frog, and I have this friction, right? So let me move it up and draw it over here, static friction. So those are all the forces, and it's often easy to look at gravity in two different directions for a ramp problem. So I'm going to break that down into weight in the y direction and the component of weight in the x direction. So after I break it down, I will cross out my weight, showing that I have already considered this force. I don't need to double count it. And this angle is the same angle as your ramp. So if this is theta and that angle is theta. So we know that weight x is weight sine theta, which is mg sine theta. Weight y is weight cosine theta, is mg cosine theta. Okay, so balance out all your forces in the x and y direction. You will say, well, all the forces in the x direction should equal to 0, which means there are two forces only, right? In the x direction, you have the friction, positive direction. You have weight in the x direction, that is negative. They add up to be 0. So static friction in this case is equal to mg sine theta, okay? And of course, the y direction cancel out. You have normal force minus the weight in the y component is equal to 0. So your normal force is mg cosine theta. Okay, so you can see static friction in this case will depend if you increase your angle theta. So if you're just sitting still on flat, you will have no static friction. You will raise it up a little bit, then you increase your angle. So you increase your static friction. But as your angle goes up, more and more up, right, bigger and bigger, you need more of a static friction in order to prevent slipping. So at some point, if your static friction cannot provide that mg sine theta of a force, then it's going to slide down. Okay, so that just shows you static friction can vary depending on the situation. But kinetic friction is always proportional to the normal force. So mu k describe the coefficient describing what kind of frictions, what kind of surface you have. It might be very smooth or maybe very rough. So you have a coefficient. It's always smaller than 1. It's always point something. Normal force in this case is mg cosine theta. So right, so if you want to know, well, if the frog is sliding down, then what is the kinetic friction? You will say, well, that must be mu k mg cosine theta. So you can see how you calculate static and kinetic frictions are different. Static frictions can vary, and we talked about how there is a maximum amount, right? There, it makes sense. You cannot provide infinite amount of static friction. The maximum amount, however, has a very similar equation as our kinetic friction. The maximum amount of a static friction a surface can provide is the static friction coefficient times the normal force. So mu of n is different from mu of k. They are close, roughly close. For example, if a surface is rough, then both the mu coefficient for static friction and coefficient for kinetic friction are all bigger than if your surface is smooth. But then these two are still different values. Okay, so usually if this is something like 0.4, this might be 0.3. They're not exactly equal, but the problem will always tell you which one it is. So use the mu of k times the normal force. That gives you the maximum amount the friction can provide, the surface can provide, okay? So when you're answering question, be very careful. If it's not the maximum amount, you cannot use this equation for the static friction, okay? So, so static and kinetic friction are a little bit tricky. We just need to know what condition we're dealing with. Let's practice that using this question here. So this is similar to the frog example. Let's say you have a box sits on a flat board. You start lifting the end, one end. As you increase the angle, eventually the box will begin to slide down. And which of these statements contribute to the reason that it's sliding down? Okay, we'll give you a couple minutes to discuss. So take a screenshot of this question, and I will open up our breakout rooms. Okay. Hello, how's everyone doing? And what do you think about this question?
I'm thinking that it does it decreases I'm not sure if it decreases the static friction, but right now I'm just processing why I'm processing A right now, like the component of the gravitational force parallel to the plane, because if you lift the board, like it points straight down.
Mhm.
Yeah, I'm thinking about the problem a little quite hard right now. I'm not too sure.
No, you're right. I think you're using a limiting case behavior. That's a common technique we use in physics. Is we can think about extreme cases where the angle is flat, or if you lift all the way up to be completely vertical, right?
Yeah.
So if it's completely vertical, you can see, well, all of the gravitational force is pointing down now, right?
Yeah.
In this case, pointing down is also parallel to the ramp, along the ramp. So somewhere in between, it would be a component of the gravitational force is pointing along the ramp, right?
Yeah.
And what is that component? What is
Uh,
the component that is pointing along the ramp?
the y, that's the y component.
That is the x component.
Oh, yeah, you're right. You're right. Oops. Yeah, that's right.
And yes, so the x component, now depending on what you label as x and y, you technically can label the other way to be your x, but in order to avoid confusions, our convention is to label the along the ramp is our x. So this is going to be our, so this is weight, and this is y, this is x, this is theta. So Wx is weight times sine theta, okay? Which is mg sine theta. So as you increase the angle theta, what happens to this component?
Well, the reason I didn't, I think the sign, like it becomes sine 0, or like it becomes sine 90 degrees, which is a, which is what was it, one, right? So does it increase the, it
Mhm.
increases the the entire thing, right? Because I don't, the reason I was just thinking about it a little bit is because gravity doesn't change it. It's always negative 9.8 no matter what.
Mhm.
So I was just thinking how it increases mg, but I know it increases mg because it equals one, 90 degrees will reach 1 for the, for sine theta.
Yeah, it doesn't affect mg. mg is a weight, it's a fixed amount.
Yeah.
It does affect sine theta. You can think about extremes. When it's completely flat, sine theta is 0, makes sense. All the gravity component is down, nothing is
Yeah.
on the ramp, but it's completely vertical. All of that component is along the ramp. So if you're in between, then you're just within 90, between 0 and 90 degrees, right? Sine theta, how does sine theta change? Between 0 and pi over 2, it always increased, right?
Yeah, exactly. Which increased the gravitational force.
Yes. So A is is correct, and it's also contributing to why it's sliding down, because whether it slide down or not is really just a competition between the force that is going down and the force that is going up. So which one is
Oh,
stronger? So this one is going down and it's getting stronger. Well, that is part of the reason that it begins to slide down. Let's see if any of other ones is correct. Component of coefficient of static friction in decrease.
Wouldn't the coefficient be constant?
Yes,
Or no.
yes. This one doesn't change, right? This is a constant. So this one what? Normal force decreased.
I would say yeah, because if you're increasing the, if you're increasing the if you're increasing the, what was it, the gravitational force, it increases the, or decreases the normal force, right? Because the other one is wg cosine theta, and
Right.
wouldn't that change as cosine like approaches 1, it approaches 0, right? Or
Yes,
as it approaches
that
pi over
does
2.
decrease. Yes, and that decrease, and that affect the amount of normal force friction you can provide. So the static friction, the maximum is this times more force. So if normal force is decreasing, the static friction, the maximum amount of static friction you can provide decrease. That's another reason that slides down. Okay. Yes. Okay, very good. I'll see you guys in a bit. Okay, I'm gonna go back to the main session. Okay, please put in your vote. Could be a reflection of what you discussed as a group or your own opinion. Let's go for 10 more seconds, okay? All right, any last minute vote? Okay, I'm gonna go ahead and end this. Let's take a look. All right, so not only we are selecting whether the statement is correct or not by itself, we also want to see whether they contribute to be one of the reasons that the box slide begin to slide down. Okay, so we can first look at whether that is true, or then we look at whether it contributes to what we're trying to explain. All right, so let's look at our distribution. It looks from the distribution, you all agreed on two of the choices, right? D and E. Both A and C are considered correct. Now, the disagreement is whether B is also correct or whether it also contributes to the scenario. So before we just try to go into the details of looking at the angle, looking at the math, what would be an intuitive way that you just explain to others? Like a young sibling, like how do you explain this to them? Why would, as you tilt something and the object which originally was staying at rest will slide down? Like intuitively, how do you explain it?
I think I would explain it more in terms of like speeding up, kind of slowing down in terms. So like let's say if you put it at an incline, for instance, you say, oh, the force, since it's speeding up, like there's more force, and like since it's slowing down, there's less force.
Okay, so when it was at rest, there's no. So originally, when it was laying flat, there's nothing is dragging it along the ramp, right? Either way. So it's just staying at rest there. But you can see that you can talk about extreme scenarios. And one of our students in our group talked about this idea that if you flip it up, and then let's think about the other extreme that you can go is from completely horizontal to completely vertical. Then you can see that you have gravity pulling it all the way down that's along the ramp. Eventually, nothing is pulling it along the ramp, okay? But then all of the gravity is pulling it along the ramp. So you have two extreme cases, okay? And also, when you flip it to this vertical direction, right? You do not have that static friction anymore. Okay, when you go all the way completely up. So we can use this because if you're here, you can see you're not pushing into the ramp at all. That normal force goes away. So you lost your static friction that the surface can provide. So let's try to break it down and look at the different force component. The first sentence said the component of gravity increase. Now we know that is Wx. Wx is mg sine theta. Okay, so as theta increase, does sine theta also increase? Yes.
Yes.
Yes, that is correct. Between 0 and 90 degrees, because that's all that matters, we're not going beyond. Between 0 and 90 degrees, sine theta always increase as theta increase. So this component indeed increased. Does that contribute to the box sliding down? So we can see whether the box slide down or not is really just sort of a competition between two forces. One is trying to slide it down, that is the weight of gravity component, Wx. is trying to make the box go down. And you have friction, right? That is try to prevent slipping. So if one of the forces become bigger, of course, it has more possibility to slide down. So I would say this statement is correct. Is one of the reasons to explain the phenomena. The second one, B, coefficient of static friction decreased. Is that correct?
I don't think so, because I kind of had a formula that I wasn't sure was correct, but it was U of S or mu of S equals tan of theta, and from 0 to 90 degrees, it's only increasing. So
Okay,
that's what I used.
yes, that is probably tangent. That's probably a sort of a equation that apply to a certain scenario. So I would discourage the use of an equation if you don't know where it's coming from. Don't use it. It's probably applicable to another problem, but it's not applicable here. So for static friction, we know first we think about, okay, what does this quantity represent? What is the meaning of this physics quantity? It represents how rough your surface is. It is a intrinsic property belong to the box and the surface as staying on. So by lifting up my my flat board, did I change the surface? Did I like smooth it up? Did I put a sandpaper on it? I didn't do any of that, right? So if I didn't change the surface, I should not have changed the coefficient. The coefficient is a constant and is an intrinsic property of your surface. So that would not change. Same for mu of K, that doesn't change. Most of our problems, we do not change the surface, so you should not have changed to mu of S or mu of K. Okay, so this statement in itself is wrong. Okay, the third one, normal force decreased. So what is the normal force? Normal force balance out weight of gravity in the y component is mg cosine theta. So as theta increase, cosine theta decrease. We do know that between 0 and 90 degrees. So normal force is indeed decreasing. So does C contributing to the phenomenon that the box sliding down? So someone might say, well, it is correct, but how does that have anything to do with the box sliding down? Normal force is in the vertical direction to the ramp. It is not a force in the x direction. So therefore, I'm not going to choose C. What do you think about that? Is C relevant or not? Anybody?
I think that C is relevant because as you're tilting, like when it's flat, the normal force is purely a vertical force, but as you tilt, it gets a horizontal and vertical component, and that would contribute to the sliding or not when you do all your force addition.
I see. So normal force certainly will tilt together along with the ramp. But if we are looking at X and Y as in vertical, the vertical direction to the ramp, normal force is always pointing perpendicular to the ramp. Even though when we are staying flat, it is pointing as a different direction, but it's still perpendicular to the ramp. When it's tilted, it's still perpendicular to the ramp. So one might argue, well, yeah, even though it has changed directions, it's still perpendicular to the ramp. So it's not going to contribute anything to the forces along the ramp. What do you think about that? Does F of S depend on normal force? Does static friction has anything to do with normal force?
It's equal in the opposite direction.
Static friction is always opposing the force that is trying to act in the opposite direction? Yes. So static friction here is try to balance out Wx. That's along the ramp pointing down. And then we said, okay, static friction, you always try to calculate it using to see which force is in the opposite direction. But when we're asking about the maximum amount of static friction, how do we calculate it? It is in the slide before this. Maximum amount of static friction is mu of S times normal force, right? So your surface can provide a certain amount of maximum static friction. The maximum amount is this fixed constant times normal force. So if normal force is decreasing, which means the maximum amount of static friction your surface can provide is also decreasing. So let's say originally you can provide 100 newtons. So as long as the force pointing down is not exceeding 100 newtons, you can balance that. But now the maximum amount of force has decreased. You can provide is only 80 newtons. So would that make it easier for this object to slide down?
Yes.
It does, right? Because these two variables both contribute. The force going down increase, the maximum amount of force you can provide going up decrease. So at the same time, both of these will contribute to explain the same phenomena. So actually both A and C is correct. We choose D in this case. Okay. So here I'm not saying static friction decrease. I'm saying the maximum amount the surface can possibly provide decreased. So it's easier for the weight of gravity to become bigger than the maximum amount of the static friction. So it eventually slides down. Okay, so it's a little, wordy to say, but we want to be accurate in our expression. So A and C are correct. All right, so hopefully after that example, we are pretty clear on static friction. Here we have another question. We tell you a box is sitting at rest. There's an angle. Mu is an intrinsic property of this surface. Simply asking what is the magnitude of the static friction right now. I'm gonna go ahead and let you vote. Just a quick check up on our understanding of static friction at this point. Okay, sorry, this one, I don't know why it showed as MS mu of S, mu of S. Okay, and let's run the clock for another 10 seconds. All right, any more votes? Okay, let me go ahead and close this. We will take a look at this together. All right, so we know that mu s times mg is not correct, because if you were to use the coefficient times normal force, the format that we're very familiar with, you need the normal force, and that's not mg, right? So B seems to be using that formula we are familiar with, that is using mu sub k times normal force. And C is the component of gravity that is in the x direction. So how come it's not, so how come a lot of you guys choose C but not B? Didn't we just use this formula in the previous case?
The reason why I didn't use cosine is because if we're looking at the static friction, we know that it's going to be the angle opposite the magnitude of the side opposite to the angle. So then if we're looking for that side and we don't have the adjacent, then we shouldn't be using cosine. That makes sense.
So you choose C, right? Is that what you chose? You see the answer you chose?
Yeah.
Okay, so you're looking at, okay, the adjacent of theta is this part, and that is the y component of our weight, and that's balanced by normal force, okay? The normal force is mg cosine theta. And the opposite side, sine theta, is giving us the weight in the x direction. So weight in the x direction is mg sine theta. So what is happening with the box right now is at rest. So at rest means sum of all the forces in the x direction is 0. Sum of the forces in the y direction is 0. Okay, so let's look at all the x and y directions. The x directions along the ramp, right? I'm drawing a line along the ramp. All of the force has to add up to be 0. There are two forces only. One is weight of gravity in x, and one is friction going upward. So they have to balance. So you can say, well, the friction has to balance that, which is mg sine theta. I'm going to choose C. When would B be correct? B would be correct if we know the static friction, or if the problem say, what is the maximum amount of static friction the surface can provide? Then you know, oh, the maximum amount I can calculate using B. But we don't know whether that is a maximum amount or not, right? All we know is it's balancing out gravity. So if it were on the verge of sliding, but it's barely hanging on there, and it's just almost going to slide down, but not quite. If we're at the critical point, so if we are at a critical point, sorry, rewrite it. Where it's just barely hanging there, almost going to slide, then what can we come up with? We can say, well, if it's barely hanging there, meaning that the static friction is at the maximum, this maximum that it can provide is barely balancing out gravity. So you would say the maximum amount of static friction is mu mg cosine theta as a normal force. At this time, it is balancing out the gravity mg sine theta. So you can see in this case, you do get mu sub s is tangent theta. That's the one you were talking about. One of you guys were talking about earlier. But that only applies when we are having this critical point, okay? When it's barely hanging on. But any time that is not like that, you do not have that same condition. So gotta be very careful what condition we're talking about here. So the answer to this question is C, because this question, all it says is the box is at rest, and we know it has to balance out the mg sine theta. So my writing is not updated. So let me go ahead and do the share one more time. Hopefully that will work. Just 1 second, please. Okay, so I was showing you how use of S equals tangent theta come from. It's coming from the critical point if you know the box is barely hanging there.
Wait, how come there's no mu in front of mg sine theta?
Because this is Wx. Wx is mg sine theta. You see which two I'm making a balance to each other. I'm saying the weight, gravity in the x direction is balancing out the maximum amount of static friction at that critical point. And this is mg sine theta. This, depending on using the formula we know, is mu times normal force, which is mg cosine theta. That's why this one doesn't have a mu. Does that make sense?
Oh, okay, I see.
Okay. All right. I know the static friction can be tricky. So any questions at this point? Any questions so far? Okay, now we'll take a little short break from doing friction. Let's look at springs. Springs should be straightforward because what we know in theory about a spring is, well, the more you stretch it, the more of a force it provides, right? The more if you can compress a spring, the more force it can provide. So the longer the stretch, the bigger the force. That's it. All you need to know is that. That's something we already intuitively know. And that relationship, it turned out to be a linear relationship described by Hooke's law, saying the force provided by the spring is proportional to how much you stretch it, how much you compress it. And there is a K, which is spring constant. That simply is an intrinsic feature of your spring. So you can imagine you have a very loose spring that have a very small spring constant. It's flimsy. Or you can have a spring that's been wired very tight together and it's really hard to stretch. That will have a big spring constant, big K. So K is really just something, a constant to describe what kind of spring you have, a strong one or a weak one. And delta X is how much you stretch it. You stretch it for 2 inches, for example. Then you put delta X equals 2 inches, or you plug in centimeters, convert to centimeters or meters. And there is a negative sign. I would say when we actually apply it in our equations, our forces will be either a positive or negative sign depending on which direction it's pointing at, right? Whether it's in the same direction as your positive or negative direction. So don't worry too much the positive or negative sign. The negative sign here in Hooke's law is showing this force is always opposing the stretch, is always in the opposite direction of where your spring is being stretched or compressed. Is a displacement of the spring. So for example, when you try to extend the spring, you are dragging your spring to the right, okay, to the right. But the force, the spring is trying to pull you back. So the force will be to the left. So therefore, when we write them as vectors, you would need this minus sign, okay? And again, the same thing about compressing the spring. If you're pushing the spring to the left, then the force would be pushing you away, would be to the right. So the force is always opposing which way you extend or compress the spring. So that's why there is a negative sign in Hooke's law. But when you apply it in your equations, figure out which way this force is pointing at, and then the magnitude is simply A times the total amount of the stretch or the total amount of the extension or the compression. Okay, so that's just Hooke's law. Let's do an exercise real quick so we can use Hooke's law in this scenario. So here, a spring stretched 1 inch when you load 2 pounds on it. Now you add another 5 pounds. How much will the spring stretch? So you probably can even do this using a simple proportion, but I'll try to put the Hooke's law in there and then do the spring constant. So what happens when you hand, this is a spring that's not being stretched at all. It's at equilibrium, right? When you put something on it, you can see it extends and goes down. So how much it is being stretched right now is 1 inch. And you put a 2 pounds of object on it, that's the weight. So what is the spring force in this case? The spring force is equal to how many pounds?
7.
So here I'm putting my 2 pounds weight only.
So then 2.
Yes, 2 pounds, very good. Okay, now let's do the 7. Now let's put 5 more on it and it becomes like this. This is 2 plus 5, 7 pounds. And now I have another spring force and that is 7, very good. Okay, so now it's being stretched even more and we want to know how much is it being stretched right now. And so how much is being stretched is again compared to where it was completely relaxed. So we wanted to measure from here to here, okay, from here to the beginning, not to where the 2 pounds was, but to the beginning. Now, how much does it stretch? We don't know. So let's calculate it. So when it was at 2 pounds, we know using Hooke's law, the spring force is proportional. So I'm just looking at absolute value here because I don't really care about the two are in different directions. I only care about the magnitude. This spring force is 2 pounds and it's being stretched for 1 inch. So 1 inch. So spring constant K is 2 pounds over an inch. So even though the units is weird right now, but that's okay. We're gonna leave it as it is. So spring constant K is 2 pounds per inch. Now we have 5 pounds. So right now we have 7 pounds, 5 pounds added. The same spring, right? We're using the same spring. So you're gonna plug in the spring constant, which is 2 pounds per inch times how much is being stretched now. I don't know. And that's the one I'm trying to look for. Okay, so let's look at this. You can cancel out the pound as a unit. So delta X is equal to 7 over 2 inches, right? And that is 3.5 inches. So D is correct, 3.5. Does that make sense? You can see this is also a simple portion. Okay, 2 pounds make it stretch for 1 inch. How much would 7 pounds make it stretch? And you can see that will tell you it's going to be 3.5 inches. Okay, the proportion is exactly K here. But here I simply applied Hooke's law 2 different times. I calculate the K and then plugged it in to find how much is stretched now. So that's all we need to know about the spring. So I think for spring, it's more straightforward than the friction, right? It's just the longer the stretch, the bigger the force, and it's a linear relationship. So 3.5. So in the application of Newton's second law, a lot of times you will see these very classical type of problems. Looking by the surface, looking at the surface feature of these problems, sometimes they involve a ramp, okay? Sometimes involve a spring. Sometimes involves a rope extended through a pulley. You have a tension and pulley problem. Sometimes involves multiple objects with one right next to another. Sometimes you need to use both the Newton's second law and kinematics combined to solve these problems. So let's get more familiar with these different contexts. So when we see these similar type of questions come up, we would know how to tackle it. But the key is you're just applying Newton's second law into all these different scenarios. Even though they may look different, the physics is still the same. So we'll start with a problem that involves both the incline and the spring. So I think that's a good problem because it involves these two different kind of, we can practice these two different kind of features. Okay, so let's look at them. So here we have, again, a box sitting at rest on a ramp, but the only one extra element is that we added a spring. The spring is now also pulling on the box or connected to the box. So we know the mass of the box, we know the angle, we know what mu of k is. So that is the surface, how rough or how smooth the surface is for the kinetic friction. The static friction is also given, is slightly different. Okay, so and then we have a spring here attached. The question is, what is the minimum spring constant that you need, the kind of a spring you need? Let's say if you just put the box there, so it's going to slide down. So you think to yourself, okay, I'm going to choose a spring so that the box does not slide down. But you don't want to use a spring, a stronger spring than you need. You want to find the bare minimum spring constant that can prevent this box from sliding when the spring extended for 12 centimeters, 0.12 meters from the relaxed state. Okay, so the key here is what is the minimum spring. So what do you think that implies? So let's, we're not going to be able to finish solving problem, but qualitatively, let's analyze it before we end the class today. So, so here we wanted to really think about what it means by the minimum spring constant you need. So if I ask you, okay, let's draw the free body diagram. All the other forces we know how to draw, right? We know gravity, we know normal force, and which way is the spring force? I also need the force from the spring, and I also need static friction. Let's do it one by one. How do I draw the spring force?
Is that in the positive x direction?
Is it up along the ramp, right?
Yeah.
Yeah, so if the spring is extended down, then the spring force will try to drag you up. Right, so I know this one, spring force must be up along the ramp. It's preventing sliding, yeah. Okay, how do I draw static friction? So what is the direction of the static friction? Is it pointing up along the ramp or pointing down along the ramp, or depends, or neither of those? So which way should I draw my static friction? Should I draw my static friction this way, or should I draw my static friction this way?
I may be wrong, but I think it depends on if the spring is like, because right now we have the force from gravity and the incline on the box that's kind of pushing it down.
Mm-hmm.
And then we have the force from the spring. So depending on which is greater, that'll impact the friction, because it'll be the opposite of the direction of which is bigger from the other two.
Okay, that's a very good thought. But this goes back to your purpose of the problem is you're trying to find the minimum spring constant. You're not going to give it more than it needs. So if you're trying to find the minimum spring constant, you're sort of like letting it slide, you kind of hold it and let it extend it a little bit. And so in that process, your spring force is always pointing up. And you probably also try this. You can try an error method. You will find, okay, use a weak spring to begin with and increase the strength of that a little bit. You're not going to give it more than it really needs. So you can see that in what scenario would make your spraying force as a minimum. So you want to have a minimum spraying force. So if f of x pointing upward or f of s pointing downward, which one of those is going to give you a minimum spring force? So spring force, if your friction is pointing down the ramp, then your spring force has to balance out friction and weight of gravity component, Wx. If your spring force, if your friction pointing up along the ramp, then your spring and your friction together will balance out Wx. So which of these cases will give you a spring force that is the minimum?
And when it's up the rim.
When it's up the ramp, very good. So spring force wants to be, I will pull in my weight as minimum as possible. I'm going to have someone help me. So it needs someone to help him. So it needed a friction. So if only the friction is upward, then the spring force could bear it to be a minimum. So and because of the problem set up in that way, so we know that the static friction has to be pointing up the ramp. Okay, you can have a scenario where you can probably like extend the spring a little bit more down below, where the spring force kind of a little bit more up the ramp. But in that case, you can have a static friction down the ramp to balance that out, but we're not talking about that scenario there. Okay, all right, so that's all for today. Wednesday we will continue to finish solving this problem, and we will do a little bit more of the different scenarios that I mentioned previously. All right, I'll see you guys on Wednesday. I want to let you know I do have class right after this class on Mondays, so it may take me a little while to get my notes and videos up. But I always try to do it as soon as I could. Okay. All right. Bye, everyone.
Thank you, Professor.
Bye-bye.
Bye, Professor. Have a good day.
Have a good day. Bye, everyone.
Professor, I had a really quick question.
Yeah, of course.
So then, since for this particular problem, normal force didn't really like, static friction wasn't in the opposite direction of normal force. When do we know when we could apply that logic?
But this
Because
question,
yeah, because I was kind of confused.
so static friction we have already talked about. Static friction has to be pointing up the ramp. So it's in tendency, it is going to slide. So it has a tendency to slide down because the weight in the x component, because of Wx. So yes, static friction in this case is pointing opposite to the tendency of sliding down, which is up the ramp. So it is opposite to Wx.
Okay. So then Wx would be our, if I'm not mistaken.
Is mg sine theta.
Okay.
That's from the geometry of this, right? Remember, we did the angle here.
Oh, okay. I got you. Okay. So then, because of that, that doesn't mean that it's always going to be, because the way I thought about it is that since normal force is pointing upwards, then automatically the static friction needs to be pointing downwards. So then in this case, because we're going up the incline and we're finding the minimum, it should be pointing towards the direction of the spring, correct?
Right, it actually has nothing to do with normal force. Normal force is always in the perpendicular direction of your static.
Right.
It doesn't affect which way your friction points. It may affect how much of friction you have, but it doesn't affect in which way your friction is.
Okay. Okay, I see. All right, well, thank you, Professor.
You're welcome. I'll see you on Wednesday.
See you Wednesday. Will you still have office hours today?
Yes, of course.
Okay, thank you.